Great, thank you very much, Joe. Okay, Mike, the floor is yours.
Yeah. Thank you, Elad, and thanks, folks, for the time. So we've got a lot of content for you today in the half an hour. We're going to go through like an interesting telco edge networking for Kubernetes concept and architecture and use case with you, and then we're going to give you a brief demo as well. Right, so it's a joint presentation between myself and John Griffin on the Intel side, and Jan Scheurich on the Ericsson side. So let's move on. So just to give you an overview first, and then I'll hand over to the guys, right? So we've been working on a proof of concept together, Intel and Ericsson. And as part of that, there's been several IPU-based use cases that we're working towards. So one of them is telco edge networking for Kubernetes, which we're going to do today. We're also working on other things, not covered today, but maybe at some future time. We're working on remote manageability for an IPU particularly in edge settings and the node and server considerations there. And we're also working on things like end-to-end network security. So for today's focus with respect to Kubernetes, what we're addressing is both primary and secondary networking. But from an acceleration perspective or / an offload perspective, we're focusing on accelerated secondary networking only, right? So we're not accelerating the primary Kubernetes networking. So the secondary networking, as we know, is very critical for telco use cases. So that's number one. The second thing is that we feature an integrated edge router. We refer to it as an EVPN gateway. That's how we've labeled it. So that's part of the concept we have, and we also feature a support for a managed underlay on the IPU, and we'll discuss that in the architecture description shortly. Everything we're doing with respect to the proof of concept is based on open source control planes, several of them, and we'll describe those as we go on. And lastly, of course, the whole thing is based on an open architecture with standard interfaces. And we do have a goal jointly, between ourselves, Intel and Ericsson, to contribute vendor agnostic code to OPI. So with that, let me hand over to John Griffin, and we'll start proceeding.
Thanks, Mike. So if you go on to the next file, Mike, please. So this slide actually shows kind of a typical network scenario we'd like to deploy into. So on the right-hand side, in the green workloads, is a single server deployment. So an example use case could be Cloud RAN or some other local edge gateway. And all these will be virtualized using Kubernetes networking. So obviously these sites need connectivity, network connectivity between themselves and to some central server shown as a P router there in the data center. So in between these sites, there can be, arbitrary transport networks. We don't necessarily implement those, of course, and we can choose the technology they run on. And really, the only common factor we need is that they transfer IP packets for us. So I guess our main requirement is to create an overlay that only relies on the IP transport in the underlay. Another requirement that's key for us is traffic separation. So that allows us to give separation between logical networks, and that also increases security. Another key feature, I guess, of that is that it allows for overlapping IP addresses. So we've actually implemented this as, a VPN, virtual private network, and the EVPN gateway that Mike was talking about. That really allows us to have L3 routing to the transport, and it also serves as an endpoint in that VPN implementation. Down at the bottom there in the blue box, I guess our overall goal is to reduce down the size of the small site locations, and we'd really like to get that down to a single server and all of the networking offloaded onto the IPU. So obviously this has cost benefits, cost savings, because it avoids the need for having to deploy dedicated networking equipment at those small sites. So next slide, Mike. So I actually, to implement that VPN that I talked about previously, there's multiple technologies we could have used. So for example, traditionally you could have implemented BGP paired with MPLS, but we actually decided to use EVPN. It's standardized by the IETF and is widely used in data centers. And it actually fits our use case quite well. Originally it was for L2 VPNs, but it's been updated for L3, and that's exactly what we needed to do. It provides, logical L3 VPNs on top of existing IP networks, and that was a very good fit for our proof of concept here. So we decided to go with that. And if you go on to the next file, Mike, it kind of describes, how EVPN does it. It uses BGP in the control plane. It's well known. It allows the network to be flexible and extensible. Actually, on the IPU itself, we've an implementation of BGP, and that can communicate with the provider edge router in the data center, and it's interoperable, I guess, with any of the gateways that come from the major vendor players. So that's on the control plane, on the IPU. In the data plane, EVPN itself uses VXLAN, and that isolates the tenants from the underlay. Can also route IP traffic, so we don't need to depend on MPLS in the transport. We obviously can't assume that we can trust the connected networks, so everything is encapsulated in an IPsec tunnel. So this obviously gives us encryption as well as authentication. So next file really gives a breakdown of the implementation. You can kind of see the network elements in this slide. So basically we've two layers of routing. We have the tenant routing, and that's kind of shown there in the middle with the green and blue boxes, the VRF boxes. And it contains the routing information for all the VRFs that are inside the tenant networking. Below that, we have the underlay routing, which we've labeled GRD here in the diagram, which stands for Global Routing Domain. And that obviously allows the IPU to connect to a PU router or to another edge gateway. At the bottom, as we mentioned before, everything's encapsulated in IPsec, ESP IPsec, and that ensures the confidentiality and authentication of packets. Right at the top there, you have the Kubernetes, actually, sorry, Mike, just right at the top of the Kubernetes pods. And, they're allowed to communicate to each other over an L2 bridge, the tenant network bridge. So that's kind of an overview of the network elements. I can hand you over to Jan now for Ericsson, who will walk us through the architecture.
Yes, thank you, John. Mike, if you could stop sharing, then I can start myself. I can't just take over. Okay, let me see if I manage this. Can you see my screen?
Yes.
Yeah, can see it.
Oh, very good. So I'll guide you through the POC design next, and before we go on to the actual demo. So this is a graphical representation of our architecture. On the top, we have a single server host, which is running a standard Kubernetes system. We have the Kubernetes control plane with kubelet. We have the standard primary networking realized through Calico CNI and kubeproxy. Both are relying on plain Linux routing and IP tables on the host for the primary networking locally on that host. Then for external connectivity, the host is connected through a primary virtual function to the network interface card, our IPU. On top of that, and Mike has already mentioned this, the focus of this POC has been on secondary networking and accelerating secondary networking. We have Multus with a secondary CNI plugin, and that secondary CNI plugin plumbs in virtual functions as secondary network interfaces into Kubernetes pods. They are consumed as standard SRV virtual functions by the pods. They can be configured in two ways: as access virtual functions providing untagged traffic access to a single network, or as trunk interfaces providing VLAN tagged access to multiple networks. I'll come back to that later. Then the IPU connects those virtual functions through a programmable P4 hardware pipeline to the physical ports. And the hardware pipeline has several stages. It has at the top a VLAN aware L2 bridging stage. It has a VRF routing stage. It has a VXLAN NCAP decap stage, an underlay routing stage, and IPsec encryption decryption. And all this is provisioned with state rules through the control plane that runs on the ARM cores of the IPU on the left-hand side. And this is Linux. And so we have several control planes there that are existing open source, Linux bridging and routing for the actual control plane and slow path implementation. We have the FRR as an EVPN gateway control plane for BGP. And we also have Strong Swan as an IPsec IKE control plane. All of these are orchestrated by a new component that we have called the IPU Infra Manager, which runs on the ARM cores and basically configures these components and translates the resulting state of the Linux system on the ARM cores into forwarding information that is programmed in the pipeline. And as you can see, a large part of this IPU Infra Manager is actually vendor agnostic. It has really no knowledge about how the pipeline is programmed. There is a kind of plugin interface here, and then there's a very relatively small component that translates this information into the format that can be then programmed into the pipeline through the vendor SDK. So the bulk of this software that we have running here on the ARM cores is actually vendor agnostic. Now, networking needs to be provisioned, and for that purpose, we have defined a new gRPC API here at the top that is used, and I'll come back to that in a little more detail, to do the network provisioning through, in our case, a simple CLI wrapper on the host, but it is also used by the CNI plugin to program the networking for the virtual functions that are being injected into the pods. So the CNI plugin that we have here is derived from the OVS CNI plugin for tactical reasons. It had the necessary support for access interfaces and VLAN trunk interfaces already defined, and it had code for managing virtual functions as pod interfaces. So it was the easiest way to use that and morph it into something that, instead of programming OVS for the forwarding plane, use the gRPC API here to program the forwarding on the IPU.
And just two really quick questions here. One is the VTAP plumbs to a L2 bridge that's mapped to the K8, each K8's pod local networking. See, you know, it's CNI forwarding. How does that work exactly? So VTAP matches K8's pod, and it's through a Linux bridge on the host?
It's maybe not such an easy question to answer. Maybe let's come back to that in the end when we have done the demo. Then maybe it's easier to explain.
We could talk about that in the API group meeting.
That's a good possibility. Yeah,
it'll match well to that meeting. Mm-hmm. Second one is you have IPsec. What are the thoughts on TLS in parallel to IPsec? So being able to do IPsec or TLS encryption, since TLS is just better when you have TCP, and VXLAN is, lovely way to use TCP.
Mm. Yeah, that's also a good question. For the use case that we are looking at, IPsec was the more natural one, but of course, other options are entirely possible here. That also then, of course, depends on the capabilities of the hardware, that whether they can actually transparently offload inline encryption on that level. Yeah, for our use case, we have focused on IPsec because that is the more natural fit for the network scenario.
Yeah. So again, if the hardware only support IPsec, you got to do that. But if it supported TLS, TLS is just flat better for encrypting TCP stream.
I don't want to argue about this. It's just that we haven't looked at it, right? So let me go on. Just wanted to
just a second. There's a question. There's a question from Vipin. Vipin, go ahead.
Mm-hmm. Yeah, hi. This is good. I have a question. You show that on the right side there's B4 hardware pipeline, and then we talked about OVS. So is it like the OVS data plane construct, or OVS DB
No.
Commands are converted into P4?
No. OVS does not play any role in there, really. Neither OVSDB nor OpenFlow. The only reason I brought up OBS is that we as a code base for the secondary CNI, we used the existing OVS CNI and morphed it into something that was, instead of talking to OVS, it's talking the gRPC API to program the forwarding plane.
Got it.
Other than that, there is no connection to OVS.
Okay, that makes sense. Yeah, otherwise it would seem conflict. Thanks.
Yeah. Very good. So let me move on. I just wanted to quickly highlight that the use case that fits very, very nicely with the scenario 2 that RedHat has defined as one, or proposed as one of the IPU DPU scenarios, where we have the virtual functions that are being injected into the pod. As network interfaces, we also can have the host using a virtual function for communication, as we use for the primary networking. We have the control plane running on the IPU. We have a high-level API, our gRPC API, to provision networking, and we have a low-level API here that basically is netlink oriented, which is used by the control plane here to actually program the forwarding. And our CNI plugin is a kind of proxy CNI plugin. Basically, it does the minimum that it needs to do, that is plumbing virtual functions as port interfaces on the host and programming them with IP address information if necessary, but then delegates all the rest to the IPU control plane through this gRPC API. So it fits very nicely with this proposal here. Looking at the API, it's a very lean API for EVPN tenant networking orchestration. It really focuses on the essential entities and attributes for the most common use case that we see. And it has only 4 objects. It has the logical bridge, which represents the local L2 broadcast domain that is exposed to tenants through the CNI. And it can optionally be part of an L2 EVPN in the WAN, but we are not making use of that in this POC currently. Then the virtual functions are attached to the logical bridges through the bridge port entity, and the bridge port connects virtual functions to one or more logical bridges. And if it's an access bridge port, then it connects to a single logical bridge, untagged traffic. If it's a trunk bridge port, then it connects to possibly many bridges, and then the client has to handle the VLAN tags inside the pod. Then we have the VRF, which is the local routing instance of an L3 VPN in the WAN, identified by the VNI value that is used in VXLAN encapsulation, and as a route target. And that you then connect tenant networks, those logical bridges, to a VRF through the definition of SVIs, switch virtual interfaces, which basically bind a VLAN ID to a VNI and assign it a gateway MAC address and an IP address. So maybe that already answered one of your questions, but we can easily come back to that later. So it's a very small API, as you can see. It's really, really simple to use for that particular use case we are after. And that brings us to our demo. We're going to show you how this works in practice. So the demo lab consists of 2 servers. On the right-hand side, we have the IPU server system under test with the Kubernetes host and the IPU. On the left-hand side, we have a remote PE realized through a test PE VM. We have FR running on the IPU. We have FR running on the test PE server. They are paired for EVPN. On the test PE, we already have configured 2 VPNs, VRF Blue and VRF Green, for secondary networking. There's nothing yet on the IPU server. So what we will do is, first step, we will provision the networking. So 2 VRFs, 4 VLANs, and SVIs to connect them together. And then we will bring up 2 pods, an access pod that has 2 access virtual functions connecting to VLANs 10 and 22, and the selective trunk pod that has a single trunk interface connecting to VLANs 10, 20, and 21. And when that is done, we'll show the connectivity. We're going to ping selective trunk pod from the test PE server. We'll also show local connectivity, both L2 connectivity on VLAN 10, as well as locally routed L3 connectivity in VRF green between the two pods. So let me then jump to my terminals. On the right-hand side, this is the Kubernetes host, where I'll execute most of the commands. On the left-hand side, you see the remote PE. And the top windows show basically just scrolling along log entries where P4 programming is shown on the top right-hand side here for programming the pipeline on the IPU. And here we see BGP updates coming in on the remote PE router as we configure things on the system under test. So don't expect to read those. I will not explain them either. It's just to demonstrate the things that are things happening under the hood when I execute certain commands here. So the first thing is to create the configuration for secondary networks, which means we create the 4 logical bridges for the 4 VLANs. We create the 2 VRFs, and then we connect them together as shown in the picture. So let me just execute this. And you can see we get BGP updates going on the test PE side. We get a lot of P4 programming happening on the host, on the IPU. And now we should already see that we have received routes through BGP. Oh, sorry, I want to show green. So the connected subnets that were defined for those VLANs, they have been propagated and they should be reachable now. But there, of course, there's nothing yet, no pods yet started. So let me start the pods as well. Starting with
Jan,
the selective.
I'm sorry, but I'll have to stop you in 1 minute because we only have 30 minutes. So I want 5 minutes for questions.
Yep. Then let me. I will just 1 more minute, okay? Then I'm there. So the pods are up and running. Let me see if I can ping the pod from the test PE. Yes, I can. And I can also ping locally here. So I have two secondary network interfaces here, and let me ping on that access pod. Let me ping from 10.10.3.3 to 10.10.3.5. On the other pod, that is working, and if I do the ping from VLAN 22 to VLAN 20 on the other pod, that is working as well. And that concludes my demo. Thank you.
Yeah, I can give a summary if we have time, or do you want
I would like to take questions actually.
Okay, let's go for
if
questions.
that's okay.
That's okay.
But then let us maybe move back to the slide that we had for the questions.
Put up your architecture slide again, John. We can use it as a frame for the questions.
Yeah, let me do that. Okay.
Okay, guys. Any calling for
sharing.
questions? Any questions from the audience?
I have a question on the API that you described using 5 objects, WRF and all those things. The question is that where you are thinking the API will be standardized, or what are your thoughts on API point of view in this demo?
Yeah, I think what you're talking about this API here, the EVPN gRPC API.
Correct.
Yeah, I think we can augment the, at least I know there's a proposal in OPI, to have orchestration type API. I think we need to add in, or we'd like, I guess, to add in the semantics, and I guess our summary touches on this a little bit, that we'd like to contribute the API that we have into the community. And you know, from our perspective, we'd like to augment the existing proposed API with our EVPN approach as well. So we'd like to do that, but further than that, we'd actually like to contribute, you know, as Jan described, the you know, the vendor agnostic code. You know, basically everything here that's in yellow code. We'd like
I
to
think in short, yes, John. I mean that level of API we think is one of the levels that should be in scope for the OPI standardization.
Yeah.
Can you
Okay,
share
makes
the
sense.
presentation?
Yeah,
Yes.
including the yellow code on the OVS CNI that you modified, not the OVS CNI, but the modification of that calling gRPCs APIs to DPU.
Yeah, you asking, can we share that?
Yeah.
I think we will, right, Jan, but I think it probably needs a little bit of reformatting to make sure it's upstream compatible, right? But I think that is definitely the intent to share that code. And not just that code, I think, you know, also, you know, the infrastructure manager and the IPU agent. If you know, people think that there's interest in, you know, having something like this contributed to OPI, then, you know, it'll probably take us a little bit of time to get it to upstream compatible format, but, you know, we're willing to make an investment like that if there's interest in the community.
Yeah. So is this a DPU consuming use case? By that I mean you put this on your DPU and that's its job, and we're doing other things other than maybe, you know, utility processing wouldn't be its job or couldn't be its job, just the way this pipeline is structured and the way this code is operating.
I think our POC concentrated on this particular use case. You know, we didn't really look at augmenting the use cases with this particular use case with additional use cases, but I'm pretty, you know, I'd be sure that you can augment additional use cases on it.
So I guess my real question is, if I wanted to do, you know, container to container or pod to pod forwarding through, say, an OVS instance on the DPU in parallel to plumbing remote connectivity to the pod through the basically mapping the virtual functions into the pod CNI layer through this tunnel. So this tunnel's great, but can I do both of those at the same time? Or if I'm doing this remote connectivity tunnel, then I'm cutting off other things? Or in parallel, can I have OVS with another set of virtual interfaces to do the local forwarding?
Yeah, I mean, we have shown that secondary local forwarding is already part of the scope here. I think you are probably talking about primary networking traffic, right? Pod to pod. That
Correct.
we right now in this POC we are doing this through the standard Calico CNI, so it would be locally routed and IP tables processed on the host. And is your question, can this be enhanced to also offload the primary traffic through some complementary mechanism to a different part of the pipeline, or a different pipeline indeed?
That's right. That's basically what I'm asking, because
I think, I mean, you can see here the focus for the tenant networking has only been L2 bridging for secondary, and also to do some minimal bridging for the primary traffic to be able to reach the external world through the EVPN gateway, right? But of course, you could consider splitting this and have L2 bridging as a primitive functionality, and then have the full-blown offload of primary networking, be it through OVS or some other mechanism. But then, of course, it would still have to be integrated with this remaining pipeline in a way, in order to share the external networking.
Yeah. So exactly. I'm asking, is that possible?
I think it should be possible, but of course it makes it more complex.
Sure, but then is that desirable? So it seems to me that would be desirable.
Yeah, I agree.
And then in addition, you know, if I'm going to do pod to pod, maybe I want to treat my pod to pod as VTEPs, but it hairpins in the P4 pipeline.
Correct, which is how it's done on the secondary right now. So your suggestion that could work on the primary as well, which wasn't our scope here, but is certainly feasible. Yeah.
Yeah, just thinking out loud. And yes, you answered a good chunk of my question. And I typed that answer, so we don't have to dig further into that. I think I get it now.
Okay, good.
Virtual interfaces into Calico, and then it all just happens by Linux magic at that point. Got it.
So we're already beyond the time that we set, and we might lose some people. But any more questions? Last questions from the team.
Yeah, just one. Do we need to have a shim, like an IPU agent shim underneath the Calico CNI, or is it only through the secondary CNI?
Yeah, in this POC, there is nothing. I mean, we leave Calico basically as is. All the Calico magic locally on the node is untouched. It's only the external connectivity that is offloaded then through the IPU.
Right,
but if
eventually, do we think
to,
we need it?
That depends, I would say.
Yeah.
For the use cases that we've seen so far, an acceleration of primary networking, Calico or the like, is not mandatory, right? The load on that is so low that it doesn't really make sense. The investment is very large, and the requirement is not very high. Secondary is obviously needed because there we have the requirement to have millions of packets per second.
Right. Okay. No, it was curiosity mainly because I'm thinking of it in terms of telemetry and some of the other statistical information that you might want to track by, one of the K8 pods or something, and it may need to use the Calico CNI to pull in and then get some of that information out of the infrastructure in the IPU.
Okay, that is a question that we haven't really looked at. How does the cluster sitting on the host integrate with something, a control plane sitting on the IPU?
Right.
Are the two nodes part of the same cluster, or is it some external? Those kind of questions we haven't looked at yet.
Yeah, those are the questions that we're wrestling back and forth with in the API group. We're looking at it from being local, being remote, and where do you need to put different shims and things like that.
Yeah, that's a good point. So I think we can continue this part of the discussion on the details of the APIs and the structure and what components become common and what stay specific to this use case in the API group, right, Mark?
Yes, we can.
Okay.
And should we take that, Mark, in next week's meeting in the API group, or can you schedule us in to have a follow-on discussion?
I can schedule you in. If you want to do it next week, we can. If you want to do it this week, I can also fit it in. So it's either way you want to do it.
Let's try next week. I think it would be good for both teams. Yeah, I think it would be better for us. Yeah.
Okay, yeah, so I'll set it up for next week. I'll defer it from the topic today, and we'll just continue on our structure work that we're doing around how we figure out the CNI shims and things. Okay, thank you.
Thanks, Mark.
Thank you, everybody. Please share the slide deck. The team that presented, please share the slide deck with us so we can share it internally. The recording will be available as soon as Joe helps me with that one. Thank you, Joe. And we'll share that internally as well. And we'll start circulating this idea around and seeing what we can do with it. Does Ericsson have any plans to deploy this?
Not sure what you're asking.
Yeah.
Will it become real?
We'll defer that one. That's a complicated question that we probably cover in OPI. So itself, right? We can, but having this as something in parallel to Nginx, and this uses the strong swan that we already have, which is really good, and expands the components and forces our thinking on how to have a consistent set of components. This is excellent. We can't talk about what any individual company will do with it outside of OPI.
No. But I can reverse the question and say we're not just here for charity.
But yeah, of course, that should be obvious to everyone. So when people are bringing
so there is a good chance that something of this might be useful.
Exactly.
Mhm.
All right, cool.
Yeah, but ideally, we want this solution to be multi-vendor capable, so that the same set of open source components contributed through OPI or associated projects can be used not only on one IPU, but also on other DPUs with minimal vendor adaptation.
Yeah, that is absolutely key. 100%.
Yep.
That's
That
the
is
point.
the goal. That is the
Yep.
goal, and that's why I asked the question. I think that
Yep.
once contribution is done, we will work with all the vendors inside OPI to make sure that they have their own version of this running and working. And then you actually get 5 different vendors that can support this architecture.
Sounds like return on investment.
Yep, that would be great.
All right, I'm going to stop the recording now. Alon.
Thank you very much.